The dark matter hypothesis. The dark matter hypothesis was essentially established in 1974 by Oestreicher et al., who concluded that the rotation curves of spiral galaxies could most plausibly be understood if the spiral galaxy was embedded in a giant spherical halo of invisible dark matter. In the conventional cosmological model of spiral galaxies, each spiral galaxy is considered to be surrounded by a giant halo of invisible, dark, matter that provides a large contribution to the gravitational field at large distances from the center of the galaxy. Standard model of cosmology assumes that the universe is now composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, so that dark matter constitutes about 84% of the total mass, while dark energy plus dark matter constitute about 95% of the total mass energy content of the universe. Thus, for many years, cosmologists have been confronted with the notion that 84% of the gravitational mass of the universe is dark matter. The hypothesis of a dark matter spherical halo surrounding a spiral galaxy to account for the observed flat rotation curve of the galaxy has yet to be verified. One of the main difficulties is that the nature of the proposed dark matter is unknown. Initially, massive compact halo objects, MACHOs, were searched for within the outer regions of galaxies, using microlensing techniques. The conclusion from these observations was that at most 20% of a galactic halo consists of MACHOs, and the rest of the halo consists of non-baryonic matter. The only other known candidates for dark matter are the three neutrinos of the Standard Model, SM, of particle physics. However, it was demonstrated in 1983 that if dark matter consisted entirely of neutrinos, the large-scale structure of the universe would significantly differ from the observed one, since the neutrinos are relativistic particles leading to a smooth large-scale structure. Recently, Frampton has suggested that the non-baryonic component of dark matter may consist entirely of primordial intermediate mass black holes. However, this suggestion remains to be verified. The existence of dark matter in the universe suggests that one requires new physics beyond the SM. Three such particles have been searched for without success: 1. Axions, 2. Weakly interacting massive particles, WIMPs, and 3. Sterile neutrinos. These three particles are all hypothetical particles, some of which have been introduced into particle physics in order to resolve certain perceived problems. The action was postulated in 1977 by Pecchiai and Quinn in an attempt to understand the strong CP problem in quantum chromodynamics, QCD. To date, various experiments have been carried out, but none have successfully identified an action particle. A weakly interacting massive particle, WIMP, is considered to be a new elementary particle, which only interacts via gravity and any other weak force. The basic goal of direct detection of a WIMP is to measure the energy deposited when it interacts with nuclei in a detector, transferring energy to nuclei. Such direct detection experiments need to be carried out deep underground to prevent them being swamped by unwanted noise from cosmic ray particles. The most favored, WIMP, is the lightest neutral stable particle, the neutralino, predicted by the supersymmetric, SUSY, theory of particle physics, which provides a significant relationship between elementary bosons and fermions. This relationship resolves several puzzling problems, including the hierarchy problem, for example, the extremely large difference in the strengths of the gravitational and weak interactions 10⁻36. However, to date, no evidence for any SUSY particle has been found either at the Large Hadron Collider, LHC, in CERN or in the many underground detection laboratories. At the LHC, no previously unknown particles, which may be evidence of SUSY, have been observed since the claimed detection of the Higgs boson, so that SUSY probably does not exist. In addition, no WIMP has clearly been detected over several decades at any of the underground laboratories such as the Large Underground Xenon, LUX, experiment in the Homestake Mine, Dakota. However, there has been one claim of direct detection of dark matter from the Dama Libre experiment at the Gran Sasso Laboratory. This experiment has observed a possible dark matter event rate that modulates annually as the Earth travels around the Sun, while the Solar System moves within the disk of the Milky Way and hence through the hypothesized galactic dark matter halo. The count rate is expected to depend upon the relative velocity of the detector and undergoes a modulation that peaks in June, when the relative velocity is at its maximum. This observation of the Dama Libre experiment is controversial, since it has been excluded by observations from several direct detection experiments, including perhaps the most sensitive one, the Lux experiment. In order to test the Dama Libre claim, a more sensitive direct detection experiment, SABRE, is being undertaken with improved but similar equipment in Australia. Sterile neutrinos are also hypothetical neutral particles that emerged from the development of the electroweak theory by Glashow, who separated the neutrinos into left-handed and right-handed particles. The left-handed neutrinos interact via the left-handed weak interaction, while the right-handed neutrinos do not and only interact via gravity. The right-handed neutrinos correspond to the so-called sterile neutrinos. The possible existence of sterile neutrinos arose in the development of the SM at a time when the neutrinos were considered to be massless. This is no longer the case, so that the three normal neutrinos are expected to have right-handed components with the same mass as the left-handed components and hence are unsuitable as candidates for dark matter.